Alright, this is the last of 3 videos on Newton's laws of motion. In this video, we're going to talk about weight and about normal forces. Weight is an object on the Earth's surface. A weight of an object on the Earth's surface is a gravitational force exerted on it by the Earth. It is a force, so it's F equals ma, but A is gravity, 9.8 meters per second squared. So weight, W, is equal to mass times gravity and is measured in newtons. So if we want to find the weight on Earth, excuse me, we'll take the mass times 9.8 meters per second squared. Or if we want to find the mass, we need the weight and divide it by 9.8 meters per second squared. So in this chart, if I give you a mass, you should be able to turn it into weight by multiplying it by 9.8. And if I give you a weight, you should be able to turn it into mass by dividing it by 9.8. Now, when you're moving up and down, your weight appears to change based on your acceleration up and down. So imagine that you're in an elevator. Think about it. If you accelerate upwards, the elevator has to be pushing harder on you than on your weight. And your perception of how heavy you are is really related to how hard that elevator is pushing on you. When the elevator is not accelerating, the elevator pushes equal and opposite to your weight. But when it's accelerating upward, it pushes harder on you. But when it accelerates downward, it's actually moving away from your feet. It doesn't push as hard, so you feel lighter. So if we draw a free body diagram of that, your apparent weight, WA, is the vector of the elevator pushing up on you. And then your weight, which I'm going to call FG, because it's a force of gravity, is pulling down. So the two forces acting on you are the apparent weight, the elevator pushing up on you, and the real weight, FG. If we accelerate up, acceleration will be positive. If we accelerate down, down will be negative. So what did we do? We drew a free body diagram. We defined a coordinate system up and down. And now we're going to write the net force equation. F net equals ma. The sum of these two forces is what causes you to accelerate. So WA is a positive because up is positive, and FG is negative. So WA plus negative FG, or WA minus FG, is equal to MA. And if I wanted to find my apparent weight, then I would solve this for apparent weight, and it would be equal to the weight plus MA, or MG plus MA. So here's an example. What is the apparent weight of a 100-kilogram person in an elevator that is accelerating down at 2 meters per second squared? WA equals 100 kilograms times 9.8 meters per second squared plus 100 kilograms times negative 2 meters per second squared. When I add that up, my apparent weight is 780 newtons, which is less than my weight. And that makes sense, right? Because the elevator is accelerating down and pulling away from my feet and not pushing on me as hard. If I reverse this and I accelerate upward, I'm going to feel heavier. If I add these numbers and I plug in a positive 2 meters per second squared, I get a total weight of 1180 newtons, which is more than my weight. And think about it, that makes sense. If I'm accelerating upwards, the elevator is pushing harder on my feet. But what if I'm not accelerating at all? What if I'm moving upwards at a constant speed? If that's the case, then my acceleration will be 0, because a constant speed means that you're not getting any faster or slower. And so then it would just be equal to my weight. What happens, that force that's pushing up against you, that's balancing your weight, is called most of the time a force that's perpendicular to the surface. It's the surface pushing back up on you, and it's called a normal force. Take a can of tomato soup sitting on the table. It's just sitting there. It pushes down on the table with its weight, and the table pushes equal and opposite. So if I draw a free body diagram of that, the force of the table on the object is up and it's perpendicular to the table. The force of the table pushing on the object is always perpendicular to the surface. And in this case, since the surface is horizontal, the normal force pushes straight up. And it is equal and opposite to the weight. What if I pull something across the floor? Is the normal force still the weight? No, not necessarily, because think about what I'm doing when I pull something across the floor with a handle. There's tension in the handle, and I'm lifting up with a Y component, with an upward component, and I'm pulling horizontally. So that force of tension has an X component and an upward component, a Y component. The weight is being balanced by my upward force and the force of the floor. So the weight is equal to the sum of whatever the normal force is plus whatever the Y component of the tension is. It's also important to note that the force that's actually moving the box has nothing to do with weight, the normal force, or Fy. It's just Fx, right? It's just the X component of the tension. So normal forces could be equal to the weight, they could be less than the weight, or they can be greater than the weight. Looking at this example here, we have two people pushing at an angle on this piece of ice. So the ice has weight, right? If the ice was just by itself, the normal force would be equal to the weight of the ice. But since they're pushing at an angle, they each have a downward component acting on that piece of ice. So the weight of the ice is pushing into the table, and they are each pushing down with their own Y component. So F1 has a Y component and F2 has a Y component. When I add up the Y component of F1 and the Y component of F2 and the weight, all three of those forces are pushing into the table. So the table has to balance all of those. And all of those forces are going to give me the normal force. F2y, F1y, and the weight. Normal force is always perpendicular to the surface that's pushing on the object. So this skier that's going down an incline, the incline, before everything was nice and horizontal, just like a normal XY axis. But when you're on an incline, we need to rotate the XY axis so X is along the incline and Y is perpendicular to it. So the normal force in this case would not at all be equal to the weight of the person, because the weight of the person is straight down towards the center of the earth. So if we kind of draw a picture of it by representing the person as a box on an incline, you see that the weight force goes straight down into the ground, perpendicular to the ground. It has a horizontal X component and it has a vertical Y component. The vertical Y component is what's pushing the box up against the incline, and the normal force has to be equal and opposite to that component. The symmetry of these triangles gives us, if we use a little bit of geometry, the angle of the incline is equal to the angle between that Fy and Fg. So that perpendicular Fy component is equal to the weight times cosine of theta, and the horizontal component is equal to the weight times sine theta. Let's look at an example problem. So let's take this exact problem, pretend this is a skier problem. A girl skis freely down a 10-degree incline over a 25-meter displacement. What is her acceleration? So when we say freely, we mean there's no friction. And we have no friction drawn in this diagram. There's no friction, so therefore, when she slides down the incline, the only force that's causing her to slide down the incline is Fg sine theta. So the force F equals ma that causes her to accelerate is Fg sine theta. And notice we've got the 10 degrees, we've got an angle, and we've got a distance, but we don't have any other information other than, that we know F equals ma. So we draw a vector diagram, number one. We define positive and negative. We're going to say that going down the incline is positive. And then we write F equals MA and we substitute in what we know. The F that's causing the MA is FG sine theta. FG is MG. So MG sine theta equals MA. The M's cancel out. And we're left with A equals G sine theta, 9.8 times sine of 10 degrees. It's 1.7 meters per second squared. It's important to note that mass doesn't matter here. As long as it's a 10-degree incline and there's no friction, the acceleration is just a fraction of gravity. Mass doesn't matter. It could have been a 100-kilogram mass, could have been in 1 kilogram mass, could have been 1 gram mass. As long as it's no friction or friction is negligible, the acceleration is G sine theta. Here's another problem that we could have. A girl skis freely down a 10-degree incline over a 25-meter displacement. If she starts from rest, what's her final velocity? We calculated the acceleration to be 1.7 meters per second squared. Now we can use a kinematics equation to find the rest of this. VI is 0 because she starts from rest. X is 25 meters because it's in a problem. And VF is what we're looking for. VF squared equals VI squared plus 2AX. And if we put in all the numbers and we take the square root, we get a velocity of 9.2 meters per second. So, in Chapter 5, we've learned the difference between a force and a mass. A force is a push or pull, measured in newtons. Mass measures the difficulty of accelerating an object, measured in kilograms. The first law says that an object will stay in a state of motion unless net force acts on it. It could be at rest, or it will be moving at a constant velocity, unless there's a net force greater than 0 acting on it. We also learned about Newton's second law, F equals ma, and how to draw free body diagrams to solve F equals ma problems. We also learned that Newton's third law says that if object 1 exerts a force F on object 2, then object 2 exerts a force equal and opposite on object 1. Contact forces are action-reaction pairs. And they always, so if you're talking about a box on a table, the box pushes on the table pushes on the box. If you're talking about the weight of the box, you're talking about the reaction between the box and the earth. The box pulls on the earth and the earth pulls equal and opposite on the box. We also discussed forces as vectors and how to treat them as vectors. And we learned what weight was and normal force. So, that concludes our last presentation.